We talked yesterday about, we started talking about turbulent combustion, and the big difference here is that now, all of a sudden, there's a new time scale, there are new length scales, many length scales, many time scales that now interact with the chemistry. And that's partly what makes turbulent combustion so complicated. So we talked about, I tried to give you a very basic introduction into some of the issues in turbulence. And we saw that you can characterize turbulence with a length scale and a velocity scale. And basically, what this means, you have two physical units, meter and seconds. And so whatever you want to express by scaling arguments, you need to have two independent quantities. Quantities have independent physical units. Okay? So an example is that if you have u prime, a velocity fluctuation, and L, the length scale of the turbulence, then from this you can find the time scale. Okay? And so what we saw then was that two quantities that very often for us make most sense are the velocity and the length scale. So that's kind of always what we want to keep in mind. That's what we use when we want to have a physical picture. But then sometimes we use other quantities, like the kinetic energy, which is nothing else than the velocity squared, essentially. So that's not too complicated. But then, in addition to this, often we use the turbulent kinetic energy dissipation rate. Okay? And that's a quantity that might be a little harder to visualize. Units are meters squared per second cube. And really, the better way to remember this is the units are kinetic energy per unit time. It's a kinetic energy dissipation rate. Okay? So kinetic energy per unit time, that is meters squared per second cube. Right, and it turns out that in turbulence there are different scales, large scale and small scales. And then it turns out that this dissipation rate is equal to the energy transfer rate. The transfer rate of energy from large to intermediate scales, and from intermediate scales to smaller scales, and from smaller scales to even smaller scales. Okay? When the scales get small enough, then the dissipation kicks in. Which is why, because this energy transfer rate, that's the same for all scales. Which is why we often use the energy transfer rate, which is equal to the dissipation rate. So let's call it epsilon. Why we call epsilon to relate the velocity fluctuation and the length scale at each scale. Okay, so and that's what we call Kolmogorov scaling, and that's a relationship that we often use. So epsilon is equal to u prime cube divided by L. That's the velocity fluctuation and the length scale of the large scale, and that is equal to let's say a u prime k cube over lk, and that would be any other eddy of any other length scale and its associated velocity fluctuation, and that is equal to u eta cube divided by eta, where eta is the Kolmogorov length scale, or the smallest scale of turbulence. And u eta is the associated velocity fluctuation. So that's in turbulence modeling is always an important relationship. Okay, so then we at the end we said the next thing we want to do. So we want to talk about some combustion models that you find out there, models that are used to model turbulent combustion. And so that's what we want to do now. One of the simple ones, early ones here. And as a matter of fact, I told you one already. If you want to look at premixed, non-premixed combustion, you could use the Berke-Schumann solution and you solve an equation for the mean mixture fraction and the variance. We looked at these equations yesterday. There's one more little trick missing, which I'll show you later on. And then you can map this Burke-Schumann solution, which is the temperature as function of mixture fraction. And if you solve the mixture fraction as function of space and time in a turbulent field, then you can map the temperature into that field. So that's one. And now here's another one, the eddy breakup model. That's an old model here by Spaulding. And the idea here is that, as we said earlier, combustion is often mixing controlled. And so this looks essentially at the rate of mixing and assigns the rate of mixing as the reaction rate. And so this is what the reaction rate is in this model. It is equal to epsilon over k times this variance. And this variance, so this is the product mass fraction. So this model actually is meant to be used for premixed combustion. So now imagine you have a turbulent flame propagating from here to there, and then what makes this flame move forward is that the turbulence that you have mixing between the unburned and burnt gases, so that you preheat the unburned gases, and then you preheat the unburned gases up to the point again, let's say to the inner layer temperature, and then chemistry can happen and the flame moves forward. So this, assuming this process is controlled by this mixing rate, then you can see the mixing rate of product with the unburned. Then you can see what we have here, this here, is something like a dissipation rate again. That's a dissipation rate of the variance of the product mass fraction. Remember yesterday we had a model that says chi, the dissipation rate, that's equal to a constant times epsilon over k times the variance of mixture fraction. And that was just assuming that the mixing time scale for the scalar is the same as that, of the velocity field. And so this is basically what this is. And you can see this term here in the burnt. The variance has to go to 0 because the temperature is adiabatic, and then if you have adiabatic flame temperature everywhere, you can mix it as much as you want with turbulence. It will just stay the same temperature. So the temperature is maximum in the burnt, and the temperature is, let's say, the unburned temperature in the unburned. Also, that has no fluctuations, and so because that has no fluctuations, this term is actually 0 in the unburned, it's 0 in the burnt, and it's non-zero just in a little region around the flame front. And so that's how, and that makes perfect sense in that way, that the chemical source term is non-zero only in that. Okay, so the issue here, and you see this immediately, is what's the issue here? The no kinetics, okay? This does not know if the fuel is hydrogen or heptane or whatever, okay? If the fuel is diesel or gasoline, that's not here. And so the kinetics are entirely missing. And because of that, this also doesn't know if the mixture is lean or rich. Okay, that's just not in this formulation. And so that's also why it can't be used really for non-premixed combustion, but because in non-premixed combustion, the whole physics, combustion physics, are entirely different. And so there's an extension or modification of this, and that is called here the eddy dissipation model, was often called the Magnuson model, where the product mass fraction variance here is for non-premixed combustion now is replaced by the deficient species. So in the rich, that would be the oxygen mass fraction. In the lean, it would be the fuel mass fraction. And then this is how this looks like. You have now 3 different reaction rates One would be this, which depends on the oxygen mass fraction. One is this, which depends on the product mass fraction. And then you have a third one that looks like this just for the fuel mass fraction. And then the real reaction rate is taken as the minimum of all three. Okay? So that means, for example, in the rich, in rich mixture, this is non-zero, and the fuel is non-zero. This is 0 or almost 0, so this would be the reaction rate for rich conditions. This here replaced by fuel would be for lean conditions. And then you can see here also, when it doesn't burn, then you have fuel and air mixed, and then this product here would be 0, and so that would then be the smallest or the dominating reaction rate. Okay, so you see that model, is kind of put together to work for non-premixed combustion, but you also see that it's quite empirical. And then one big issue with this is that, you see here there's this A coefficient here, and there's a B coefficient here. And these two, they are not universal constants, they are adjustable constants. So anytime you do a simulation, you want to use this, you need to tune these two constants. And those of you who have done numerical simulations, if you need to tune one constant, that's kind of all right. But if you need to tune two constants at the same time, that's a two-dimensional, tuning space, and that's very time-consuming. So it's not very good to use a model like this because it just takes a lot of time to do this. But the way people use this is you have an experiment and a baseline experiment, and you tune it to that one baseline experiment, and then you do changes in the the operating point, and then you see how the results change. Now, this actually sees if the mixture is lean or rich, but it still doesn't see what the fuel is. Okay, so no kinetics. So these are both here the fast chemistry limit. Okay, another model which is a lot more complicated is kind of the other end of the spectrum in terms of how complicated the model is the so-called PDF transport equation model. And it's very, in a sense, it's very easy to understand what that model does. Because we said earlier, if you want to know what the mean of some scalar is, and this could now be NO, or it could be the temperature, it could be whatever you want, and you have the PDF of that quantity, then well, let me use the notation here with the sample space variable. That gives you the mean, okay? So C here is the sample space variable corresponding to the random variable phi, okay? So if I know this, I can get the mean. And now, let's say I have many, many scalars, okay? Then I could have the joint PDF. If I know the joint PDF of all these scalars, then I can compute, all the means. I can compute the mean density, the mean temperature, and all of that. So it's kind of knowing this joint PDF of all these scalars, that's kind of, that you know everything, okay? If you know that, you know everything. Now, that function, it looks very simple if I write it here, but imagine, think about what this function is. This is actually a scalar function, so it's a single value, okay? It gives you probability density. Okay, it's 0.2 or whatever it is, okay? But it's a function in a many-dimensional space, okay? Remember, we looked at the PDF of Z or of some scalar. That's a function in one-dimensional space. But the joint PDF of, let's say, temperature and mass and some fuel mass fraction, that's a scalar function in 2 dimensions, okay? So which means if I have a 50-dimensional, if I have a chemical mechanism with 50 species, and this is a function in 50-dimensional space. Okay, so it's a very complicated kind of a thing. But if I know it, then everything's fine. So this method has been proposed by different authors. It was really pushed forward by Professor Pope, who has made a lot of developments, wrote some really nice review articles also on this, and also he developed the numerical techniques to work with this transported PDF method. So the idea now behind the transported PDF method is, if this is all you ever want to know, why don't we just formulate a transport equation for this quantity and solve that transport equation, and then we're done. Okay? Now, you can do that. This is the transport equation. Shown here, it doesn't look all too complicated, let's say. However, again, the issue is, this is a transport equation which lives in a multi-dimensional room, multi-dimensional space. First of all, P is a function of space and time. Okay, so it would be 3-dimensional in space, and then a function of time also. But because it also depends on the sample and space variables, it is a function of, now if you have 50 scalars, it's a 53-dimensional space. Okay, so you see immediately it's very hard to solve this equation if you can't do finite difference or whatever. Okay, in 1D you can do finite difference, in 2D you can, in 3D we do finite difference. But here we're talking about 50 dimensions. Okay, you can't even store that field. Okay, so that's one of the issues with this, and that issue has been overcome. And I'll tell you maybe in just 2 words how one deals with this. But the other issue with that equation, oh no, let me first tell you what the nice thing about the equation is. The nice thing about this equation is that you see here, let me back up. So this here is actually the joint PDF of not only all the scalars, but also of all the velocities. Okay, so that doesn't solve only the turbulent combustion problem; it solves the turbulence modeling problem also at the same time. Okay, and what's nice about this is that some of these terms that are complicated, they appear in closed form. Okay, so for example, so this here would be just a time-dependent term, convection term, pressure term here, and then this is the chemical source term. Okay, and it turns out there's no modeling required for this term because this omega, that's a function of all scalars, and this here is a function of all scalars. Okay, and you see I take the derivative with respect to the scalars here, and because I have that function, this is closed. So this chemical source term here, that usually it is so hard to model, in this specific model, the PDF transport equation, that appears in closed form. However, the issue is you don't get a free lunch. There's another term that needs to be modeled, and this is this term here. Now you can imagine. So this here gives you the statistics of the whole field, velocity and scalar, at one point. Okay. Now you can imagine if I know what the mean value, or if I know what the statistics, what is the PDF of, let's say, the temperature at this point, and I know the statistics, the PDF of the temperature at that point. Let's say it's Gaussian here, it's Gaussian there. That doesn't tell me what the gradient is between these 2 points. Okay? Only if I know the joint statistic at both points can I back up what the gradient is. But you know, mixing, of course, depends on the gradients. So mixing in this model is unclosed. It's not clear how to evaluate the gradients the local gradient, because you know only 1 point statistics. And so people have proposed in the past to solve the same thing for 2 point statistics, which makes it even more complicated. In fact, that makes it so complicated that it's hard to deal with it. So that didn't turn out as being a good option. Now there are models for this term, and you might have heard some of these. One is the so-called interaction by exchange with the mean model. and that just says that, let me not go into details. Just mention these names. One is the so-called curls model, or there's a modified curls model, and so on. So there's some models that deal here with this term. Now the issue is, if we say that chemistry is limited by, that combustion is limited by transport, and here you need to model the transport term, then the fact that the chemical source term appears in closed form might not help you all that much, although it is, of course, a great advantage. And but especially when then it comes to finite rate chemistry effects or very slow chemistry, then of course this is a good advantage. Now the only thing that needs to be done is to yes.
Last time we were mentioning that we need to know in order to determine what the gradient is. Don't we already know that if we just solve for suppose we somehow solve this equation and we have the values for the site, can we just not do a naive finite difference and find the equation? What would be the problem?
Yeah, see here it is the problem. Let's say, so this is exactly what the problem is, okay? Let's say this is temperature and this is space. And I have 2 points, and I do a temperature measurement at this point. I get this. I do a temperature measurement at this point. I get this. Now, I ask you, what's the gradient? And you just take, this minus this over delta x. Okay, that's an approximation to the gradient. Now, what you have here is not this. What you have here is this. You do 1,000 temperature measurements at this point, and what you get is this. Okay, let me take the big point out. Okay, and this might look like this. It gives you some distribution. And now I do 1,000 temperature measurements at this point. Okay, and that gives me a distribution like this. Okay, what is the gradient? You can't tell because you don't know if this point and this point go together, or this point and this point go together. So it could be this or it could be this. Now, if you had the joint statistics, then you would always do both measurements at the same time, and then you would see maybe these two and these two and these two, and then you always know what the gradient is. Okay? But if you just have statistics here, and you just have statistics here, no way of telling what the statistics are.
So then the key is the ensemble average of the gradient. That's talking about the problem.
Right. The problem is right here is this gradient here. See, there's a gradient of C, and you don't have that. All you have is P of C. It's just a statistic. Okay, but as I said, there are models for this, or EMST is a more advanced model that was also proposed by Professor Prof. There are several models that try to deal with this. Okay, so the only thing missing then is to how do you solve this? Let me see if there's any mention here of this. Regular mixing, we talked about this. Yeah. So this is an equation 50-dimensional space or whatever, and you can't solve it using finite difference. And also, the equation is numerically not well behaved. So even if it's just in 2 dimensions, it's very hard to solve this. Now, what you have though, if you have combustion, we said combustion earlier. Combustion very often is fast, and if combustion very often is fast, then and it's mixing controlled, then this 50-dimensional space is not filled out. Okay, what does that mean? Let's just assume for a second the chemistry is infinitely fast. Okay, then you will see that the temperature and mixture fraction will always look like this. Okay, this is temperature and mixture fraction. They always look like this. Okay, and then fuel will always look like this, and then oxygen will always look like this, and so on. So then there is only a very small subset of all solutions that will ever exist. Okay? The only question then is, so we call this a low-dimensional manifold. This 50-dimensional space is not filled out. Really, the solution is one-dimensional. Okay, it's a one-dimensional solution. So you can imagine you will find all solutions in a one-dimensional line in this 50-dimensional space. Okay? So the question is then how to find this one-dimensional line. And the way to do this is to take the PDF equation and replace it by a so-called Monte Carlo solution. So the Monte Carlo solution, so PDF equations, they appear in many different fields in physics. And for example, the master equation is, for those of you who know chemistry, that's kind of a PDF equation. And any time you have these very high-dimensional equations, people use so-called Monte Carlo solvers. And what this is you have in your three-dimensional space here, you put little particles. They're called notional particles. And these particles, these are Lagrangian particles. They just move with the flow. They move through space. And let's say you have many millions of these that fill up this space. And then you track the path of each one of these particles. And you look at how chemistry happens for each one of these particles. Okay? And that turns out, if you do this right, and there's a theory for how to do this right, then the solution you get from, so you take all these particles now at one point, and you have many, many particles at one point. You average over all these particles, that will give you exactly back the PDF. Okay? And what's interesting now, these particles, they describe only real solutions. And because of that, they pick out this low-dimensional space. Okay? These particles, so this is a way, if you have a low-dimensional space, this is a way to find that low-dimensional space. If you don't have the low-dimensional space, if your solution really lives in this 50-dimensional space, I think then that's bad anyways. Okay? But that also usually doesn't happen. Usually chemistry behaves well and typically searches these low-dimensional manifolds. So these are the so-called Monte Carlo methods. And again, there's a theory for how to show that both are equivalent solutions. This equation and these, following these particles give you the same solution. But there's a very, very nice numerical technique. Okay, so this is a Monte Carlo simulation technique, and there's some papers here that describe the Okay, the next one here is the Laminar flamelet model, and we started talking about flamelet model a little earlier, and here there's only a short introduction. The idea here, a short introduction in the context of turbulent flows. And the idea here is to say, and that was an idea that came from Foreman Williams, to say, well, if the chemistry is often fast, then even in a turbulent flow, the length scales of the flame length scales, let's say the flame thickness, it might be smaller than even the small turbulent scales. Okay? And if that's the case, then the whole flame structure, we talked about flame structure, preheat region, fuel consumption region, oxidation region, and so on, maybe that whole flame structure is so thin that even the smallest turbulent eddies are much larger. And if that's the case, then that flame structure, it's not disturbed by the turbulence. Okay? The turbulence might stretch this or whatever, but it will not mix it up because the turbulent eddies might not be small enough to get into this flame structure. And that turns out, very often, this is a good assumption, especially in many technical applications which run at high pressure. Flames are, at high pressure, flames become so thin that that is then sometimes an even better assumption. And so this assumption of looking at turbulent flames in general as just an ensemble of stretched laminar flamelets or laminar flames or flame elements, that has been used in both premixed and non-premixed combustion. And non-premixed combustion here, Peters has first put this model forward in premixed combustion. There's a lot of work here by Professor Bray and Libby and others. So the idea here is that flamelets are thin, reactive diffusive layers. And what's the key behind this is that if these are reactive diffusive layers, that means there's a coupling, an interaction of this diffusion and chemistry. And that interaction of diffusion and chemistry, that needs to be retained, okay? Because that's a very strong coupling, and it needs to be retained. And so by solving these flamelet equations, as we saw earlier, one retains this reactive diffusive coupling. And that's the key kind of the flamelet models. The idea behind the flame, or the assumption behind the flamelet model, is that the flame is, thin, let's say, compared to the scales of the turbulence. And that requires that the chemistry is relatively fast. And so the assumption behind these flamelet models is that the chemistry is relatively fast. Not infinitely fast, but relatively fast. Okay? So if then the time scale is short, the chemistry happens in thin layers, and we saw this earlier when we talked about laminar flames. And now if this layer is small compared to the Kolmogorov eddy size, then you have the whole flame structure embedded in these in the turbulence, and the laminar flame structure is not disturbed, as I said earlier. Okay, but however, if the turbulence is very intense and it becomes very small, then the flame structure is destroyed, and this model nominally wouldn't work anymore. But under these conditions, it's also very likely that the flame extinguishes, and I try to make this point clear. Okay, so one then solves, or solves, let's say, these flamelet equations, and so then from the flamelet equation you get the profiles, local profiles of temperature in all species as function of mixture fraction, and for a given scalar and spatial rate. And if you want to use that model then in a CFD simulation, in the CFD simulation, you just solve equations for mixture fraction. You know the value of mixture fraction and dissipation rate from that in each cell, and you can go to your library and look up, what for a given mixture fraction and dissipation rate, what the local state is, what is the temperature, what are the mass fractions, and so on. Okay, so there's always in these flamelet models, there's always what I call a small scale solution. That's the chemistry solution. Okay, and then there's a tracking scalar that maps that into the large scale field. Okay, and so for non-premixed combustion, the mixture fraction would be that scalar. And for premixed combustion, the level set function G, that we also discussed, would be that scalar. So in that sense, and that's something I think is really important to realize, is that the flamelet model is a true multi-scale model, where you have a solution at the small scale that looks at the physics that happen at the small scale, which is the interaction of molecular diffusion and chemistry, and provides solution just at the micro scale. And then there's a solution at the large scale that solves for a scalar that allows you to map the large scale, the small scale into the large scale, and the large scale into the small scale. Okay, so these flamelet models are multi-scale models, so that's very interesting. Now, we'll talk about this G equation model and also the non-premixed combustion models later on in a little more detail. Here's a model that was proposed for premixed combustion, which is the so-called BML, or Bray-Moss-Libby model. Okay, and that's a flamelet model because this now assumes that the flame is infinitely thin. Okay? And so, in order to describe combustion then, this model introduces a progress variable. Progress variable is nothing else than a non-dimensionalized and scaled temperature or product mass fraction or whatever. So what this is, it is, if you look at premixed combustion, it is 0 in young burns and it's 1 in the burn. Okay? And then, you know, in the flame it varies somehow from 0 to 1. Okay? Because we assume the flame is infinitely thin, this now corresponds to the infinitely fast chemistry. So, what you can do then is you can assume or you can derive an equation here. So this is just a scalar equation for this progress variable, which you can solve. But it has two unclosed terms, which need to be modeled. Okay? You see here the scalar flux term, and you see here the reaction source. And the scalar flux term, now you would look later on at how we model the reaction source term, but the scalar flux term, that supposedly now is easy because we always say, well, scalar flux term, that is kind of a turbulent diffusion, and a turbulent diffusion, we model this to look just like a molecular diffusion, just with a turbulent diffusivity. Okay, that's what we did so far. Now, the problem though is, in many experiments, it was shown that if you evaluate this term here in a premixed, turbulent premixed flame, especially for high turbulence intensity, it turns out this flux goes the other way. Okay? It goes the wrong way. So, if you look at a flame, let's say, that looks like this. Okay, so this here is a progress variable now. We'll look at it as temperature, as function of x, and then you get something like this, and then this. Okay? Now, typically you would say there's a scalar flux because of diffusion. Which way does the scalar flux go? You all lift your arm. This way or this way? It goes this way, right? Because it goes down the gradient. Okay? The flux doesn't go up the gradient. For the temperature, that would violate what? The second law of thermodynamics, right? So what happens here is, if you evaluate this term, this is a flux term, it goes up the gradient. Isn't that interesting? Why does it do that? Does that violate the second law? No, it does not. The reason is, so we call this counter-gradient diffusion. Okay? And it means that if I just model this term as a normal diffusion term, it's wrong. It gives me the wrong sign even of the flux. Okay? Now, how does this happen? The problem here, and this is the problem very often, you know, when we do this Reynolds decomposition, not just here, also in other fields. Problem is this. We say the Reynolds decomposition goes like this. U is equal to, or T is equal to T mean plus T prime. T mean, that's the mean, and T prime, that's the turbulent fluctuation. The T prime for us is always interpreted as an effect of turbulence. Okay? However, or an effect of, you know, turbulent eddies, turbulent motion. However, you could have a T prime by something else. Let's say you have a flame that looks like this. Okay, very, very thin flame. And I do a temperature measurement right here at this point, right here at this point. And let's say, for some reason, I don't know why, that flame just moves back and forth, like a little bit, like this. Okay? You see that I measure a huge velocity, a huge temperature fluctuation. Okay? And if I say this is turbulence, and I think then that turbulence should have a turbulent transport also, it's wrong, because it's not turbulent and it doesn't cause any transport, because it just wiggles back and forth a little bit. It does not cause any transport. And that's the same here. The problem is you have a lot of heat release right here. Right here. If you have heat release, you have volumetric expansion, and that volumetric expansion goes to both sides. And if it does so, then you see a fluctuation. And seemingly that's, if you interpret this as turbulence, then you think it should be a cause of flux. But it is not turbulence. It's just very similar to this, going back and forth. It's just an effect of the heat expansion. Okay, so how to model this term now, let me just say, is also not trivial. And there are models for that, but the key here is to take out the parts that are related just to this heat release and the parts that are related to the turbulence. Okay, so that's kind of discussed here, I think. Now, the second is how to model the source term. And for that, we can ask ourselves the question, why does a turbulent flame burn faster than a laminar flame? Okay? Let's say the flame is infinitely thin compared with the small scales of the turbulence. Okay? Then I get a flame, maybe, that looks like this. Okay? It's very thin, and it burns in this direction. Why does the turbulent flame burn faster than the laminar flame? Because it has a larger surface area. Okay? Because if I would just say, I have a certain, if I would just say, I want to compute the mass flow or the mass burning rate, let's say, then that mass burning rate, and let's say this is a front that moves with a burning velocity SL, then the mass burning rate per unit time would be rho unburned times times SL times the area of the flame. Okay? And if you have a pipe, let's say, or a channel, okay, and you had a laminar flame like this that would burn like this, then this would be just a cross section. But if you have turbulence that does all of this, you see here that the surface area is larger, and because of this, this would now be a larger surface area, and you see the mass burning rate per unit time will be larger. Okay? So this burns faster because it has larger surface area, and so this is exactly what this is. This is what this model is. It's not, in that sense, you could say it's not even a model really, because all it does here is exactly what I have here. So this is the mass burning rate per unit time and volume. Okay, and then here I have rho unburned SL times I naught, let's say. And the sigma here, that's the flame surface density. That is the area, the flame area per unit volume. Okay? So this is just what we have here. Only difference is we have this I naught here. This is the stretch factor. You can look at the SL times I naught. We said earlier the burning velocity is actually the unstretched burning velocity, but then usually or very often it's a little faster because of curvature and stretch and all these effects. And this I naught is just a factor that corrects for all these effects. So you could look at this as a modified laminar burning velocity, basically times the density times the flame surface. Good, that's interesting. Now the question is, of course, what's the next question? How do we get the flame surface density? And there is this model here by Handel and also others who derived an equation here for this flame surface density, and they closed the equation also, and this is how the closed equation looks like. And what you see here, the equation depends only on sigma itself and c, but we have equations for sigma and c, so problem is closed. Okay. Interesting here. Let's see. This is a turbulent transport term. This here is a production term. So this is production of flame surface, and this here is consumption of flame surface by burning. Okay. So how do you produce flame surface? The turbulence. You have say you have a flat flame like this. You have a turbulent eddy like this. Then what this will do? It will do this, right? So, you know, it's the interaction with the turbulent motion that creates flame surface. And that's why there's a turbulent time scale here. And then what consumes flame surface is just the burning itself. We call this the kinematic restoration. Okay, so this looks like this. Let's say I have a flame that looks like this. And let's say there's no more turbulence. Just let this go. Okay. Then a little later, you know, it will look like this. Let's say. And then a little later, these guys here will burn out, and it will look like this. Okay. And a little later, it will look like this. So just the act of propagation just takes out this flame surface, and this is what this term here is supposed to be. Okay, so this is a model, interesting, and we said earlier there was this other model, what do we call this, the eddy breakup model. We said that's independent of chemistry. Does this model here consider the chemistry? Does it know what fuel you're using? It has the burning velocity. That doesn't answer my question. Yes or no? Yes, okay. Now, the model tricks you a little bit. Okay, it has the burning velocity. But now look at this. In order to solve this equation here, oops, the C equation, all we need is this. Okay, omega. That's it. All we need for omega is this. Now take SL times sigma. Make that one value. SL times sigma, I call this alpha. Okay? Now, all I need is to compute alpha. Now take this equation and multiply the whole equation by SL. And here I get SL times sigma is alpha. Right? Alpha, 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 alpha squared. Okay? So I can solve this equation for alpha without ever specifying the laminar burning velocity. Okay? It doesn't appear anymore. It's just equation for alpha. Once I have alpha, I can put it in this term here, and I get this. So this model, although it looks like it knows the fuel, it doesn't. It does not know the fuel. Yes?
How are boundary conditions around the way they take this
the boundary conditions, you would say, yeah, you would say the boundary conditions for alpha are that, let's say I have a combustor here like this. There must be an outflow here. Then, and the flame looks like this. And actually it is all zero on all boundaries, except for maybe here. But it's hard to specify boundary conditions at this singular point anyways. So you need to provide something that stabilizes the flame there, probably. But otherwise, usually you don't have the flame at the walls, or you don't cut the domain where you have the flame. So usually boundary conditions zero. Okay. Good. So you always got to be careful with these modelers. Okay, so the next part here is on combustion models for large eddy simulation. And I want to just briefly show you some of the special features or differences that you get by doing large eddy simulation. One of the issues we said earlier is that in LES, in RANS, here the effective turbulent viscosity is always orders of magnitude larger than the molecular viscosity. And so this means you get a very, very smooth kind of a solution, usually, compared to the real solution. And that's right, because you know, the average is just a, even if you take measurements, then the Reynolds averages, they are very smooth usually. Now, the issue is that this very often suppresses large-scale instabilities that might be dynamically important. And the other issue, I mentioned this yesterday or the day before, is that in LES or for combustion, very often very rare events are important. And so we don't, in RANs, you can consider these very rare events. So it's one of the reasons why one would do large eddy simulation. So for those of you who don't know, this is how large eddy simulation roughly works. In RANs, we do an ensemble averaging. Okay, so at each point in space, let's say you do 1,000 measurements, and then you take the mean, you know, all of these. That's basically the solution you get. In LES, you do a spatial filtering, and the idea behind it is this. A turbulent flow is, you know, very complex, and ideally, maybe you would do DNS, direct numerical simulation, resolving all the turbulent scales, all the flame, and all of that. And that, if you have a good chemical mechanism and a good code, that should give you the right answer. The problem is you can't afford it because turbulence, especially at high Reynolds numbers, has many, many length scales, and you can't afford to solve all of these. As a matter of fact, real DNS, even if they're very, very large, you'll see some this afternoon, you know, they're typically for a very small volume. And so in LES then, we just try to filter as much small-scale stuff out until we can afford to resolve the rest. Okay? And so this is the idea then here. Let's say you do a velocity measurement here in space. So this would be at one time, okay, but a spatial velocity distribution. So this would be the red line here, that would be the real measurement, or the real signal, okay? Now in LES, we do a spatial filtering, filter kernel that's applied to this field. And you take all this small-scale information here, you filter this out. So what you get then is the black line. And the black line, you see, if you wanted to resolve the red line, you need many, many, many measure points, okay? But if you want to resolve the red line, the black line, you need a lot less, okay? And so we make the filter so large that whatever's left over, we can resolve this on a mesh that we can still afford to use in a simulation, okay? What's interesting about this is now this. What have we done to the spectrum? I showed you the spectra yesterday. And to say this again, this here is kind of the energy that you get per wave number. High wave number means small scales. So these are the large scales, these are the small scales. And the other thing that was important here is a logarithmic scale. So this means that the kinetic energy, or basically all the kinetic energy, is on the large scales. Okay? This here, because it's a logarithmic scale, this goes exponentially, gets exponentially small here. In reality, and this doesn't have much energy. And so if I resolve all the energy containing scales, that means, you know, I get a lot of the dynamics of the flow. I should get that right. And all these small scales, they shouldn't be dynamically very important anyways. Okay? So that's the idea. You apply a filter here, and you filter out, you cut out all this small scale information, and then you just solve for the large scales. Now there's one more thing that makes LES attractive, and that is, or makes this approach maybe more attractive. I didn't say that yesterday, but you know, the Kolmogorov theory finds that the statistics of turbulence in this range here, in the, well, actually all the inertial range and the small scales, in the spatial range, they're universal. What does that mean? If you do a measurement here, and you measure this here, right in this room at this point, you measure this spectrum, okay? You get a curve, and if you now normalize this, non-dimensionalize this with Kolmogorov scales, okay, you have your spectrum. And now You take a rocket and you go to the moon, and go to the sun and measure the solar winds or whatever. You do a turbulence measurement there. You get a spectrum again, and you put these on the same plot, they will be exactly the same. Okay? You can do this on the moon or in the sun or wherever you want to do in the world. These are universal, and that was actually shown not by experiments in the sun, but by many, many different experiments, for many different configurations. You kind of see that once you get to the small scales, the turbulence forgets where it came from. It doesn't know if it was produced by a rocket engine, or it was produced in a boundary layer, or it was produced here by a flow over this chair. Okay? It doesn't. Once it gets to the small scales, it doesn't know that anymore. And so this means if this is universal, it must be much easier to model this. Okay? Now in combustion, it's a little more complicated again, because you have heat release. That heat release takes place because of mixing, molecular mixing. Molecular mixing is important on these scales, and so the heat release also kind of, is important on these scales, and you mess up the turbulence by the heat release and all of that. So, combustion is a little more complicated. The other thing that this shows is LES particularly good for combustion? And the answer is it doesn't seem so, because combustion happens at the small scales because it relies on molecular mixing, and the small scales here, they have to be modeled anyways. You don't resolve any energetic parts of the chemical source. Okay? If you would do the energy of you plot here the energy of the chemical source term, it would look like this. Nothing, 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 and then it has a peak here. Okay? So why do we do LES for combustion then? Turns out that in combustion, scalar mixing is very important. Okay? Large scale and small scale scalar mixing. And it turns out also that scalar mixing is described with much better accuracy in LES. And then also in LES, you resolve the fluctuations of the scalar mixing, and you also resolve some of these very rare events. Okay? You resolve some of these, you have small, little mixing, little mixing, little mixing. All of a sudden, you get a burst of a lot of mixing, which might mean your flame extinguishes or whatever. And in LES, you capture some of these events. Okay? That's why, because scalar mixing, and in particular the scalar dissipation rate, is predicted much better than LES. This is the reason why LES also gives very good results usually for combustion problems. Now, the modeling, because there's nothing resolved, everything needs to be modeled. Because of that, the models we use for RANs and LES, very often they're quite similar. But in LES, you have opportunities that you don't have in RANs. There are certain things, information that you have in LES that you can use to model combustion, and that also gives you an advantage. Okay, so the small scales, they need to be modeled, and we call these models here the subfilter or subgrid models. Turns out that the unclosed term that you get in the filtered equation, in the LES equation, it looks just like the Reynolds stress term, and it's usually modeled in a very similar way as the Reynolds stress term. What's interesting though is that in the Reynolds, in the model we had for the Reynolds stress term, we used this eddy diffusivity model, and you can use that here also. And then the eddy diffusivity model, we said the eddy diffusivity, that's equal to some coefficient times epsilon squared over k. Okay? And that coefficient, that again is a tuning parameter. Now it turns out here in LES, there is, you have a lot of information about this resolved turbulence. And that information that you have of the resolved turbulence, you can use that to determine what these model coefficients are very often. Okay? And that's called then the so-called dynamic model. Okay? The idea behind it is this. The black line here, that's the solution of your LES. Okay? But now you can say, if I would apply my model to that solution, it should also hold. Okay? The model I use for the unresolved part, it should also hold for what I resolve. I don't use it because I resolve it, but if I didn't, you know, it should work also. But now I do have the true solution. So from the model and the true solution, you can back out what the coefficient would be, you know, for, you know, this solution here. And then you just use it. So you determine the coefficient here in the resolved part, and then you use it for the unresolved part. So that's the so-called dynamic models, and they're very powerful because they're very accurate very often. And also, and that's probably the main advantage, these so-called dynamic models, they know when something funny happens. For example, if a flow becomes laminar all of a sudden, okay, then you have a turbulence model. That turbulence model has a constant coefficient. That would always say you have turbulent mixing, you have turbulent mixing, you have turbulent mixing. If the flow is laminar, you don't have turbulent mixing. Okay? In this case, if the flow becomes laminar, it would be all a straight line here. And the model would then say, hey, my coefficient has to be 0 because there is no turbulence here. And then you would apply the 0 coefficient here, and so the model knows. Or when you go close to a wall, in wall-bounded flows, you go close to a wall, the turbulence gets less and less and less. And as you know, when you right at the wall, you know there are no turbulent fluctuations anymore. And this model is able to, dynamic models are able to see that. Can we use dynamic models for the combustion source term? No, because there's no resolved part of the combustion source term. Okay, so the dynamic models, they help us in scalar mixing, but not in the reaction source term. Okay, let's see. So I think I mentioned all of these things. I want to show you 2 examples here really only for differences between what you get with RANs and what you get with LES. This is an example. There's a simulation of the so-called Sandia D flame. Sandia D flame, some of you might have heard of this. That's an experiment that was done by Rob Barlow and Sandia Livermore. And there was a workshop of turbulence modelers that has established around, initially around this data set. What was nice about this, that everyone in the world who does turbulence or combustion modeling did simulations for this configuration. And then once every 2 years, that group meets and discusses the results, puts all the results on one plot, and sees who gets the gold medal. No, there's no gold medal, but just looks at what are the discrepancies and why we have these discrepancies. So it's very good. It's called TNF, Turbulent Non-Premixed Flame Workshop. It's usually held now in connection with the Combustion Symposium. So this here shows the temperature distribution. This here shows the scale and spatial rate. Distribution. Interesting is that from an LES, and interesting is you see here that the scale and spatial rate distribution has real structure. You see high regions of high dissipation rate. They appear here in these thin layers. Looks like a Christmas tree, right? And what's interesting then also is we know if the dissipation is very high, you get a lot of heat release and so on, and you can map that into this temperature. Now here on the right-hand side, you see predictions and experiments. The experiments, of course, are the symbols, and the predictions are the lines. And there are 2 different, so red is temperature, blue is NOx. Here we have CO, and this is H2. And so it's plotted here as functional mixture fraction. This is for I think, you know, a cross-section here close to the nozzle, but that doesn't matter very much. The main point here is this. So these simulations, there were 2 simulations done, and they're shown here in these plots. First simulation would take all the parameters that you need in the combustion model, which is mainly the dissipation rate, and it Reynolds averages this parameter, and then feeds it into the combustion model. This is the best thing you could ever do with RANs. Okay? And then the second one notices that the dissipation rate is a fluctuating parameter. It fluctuates in space and time, and the combustion model makes use of these fluctuations. Okay? It's the only difference in these simulations. And what you see here is that the temperature actually is predicted by both of these in a very similar way. NOx is predicted, in a very similar way. There's not much difference. The only difference you see here is what I call the RANS type model, where we only use the Reynolds average dissipation rate. That has a slight over prediction here in temperature on the rich side. Okay? Now if you look at CO and H2, you see that this little over prediction temperature, it translates to a huge over prediction here in CO and H2. And so what's happening here is that the fuel, so the experimentalists, because they want to do Raman measurements, they cannot have any pHs in the aromatics in the field. So they premix the fuel with some air already. Okay, so they mix some air in the fuel just to make sure you don't get any aromatics. And so this is the fuel stream, and it turns out that a very weak, rich premixed flame starts to burn here in the simulation, not in the experiment. Okay, and once you consider the fluctuations of dissipation rate, turns out dissipation rate does this, fluctuates, and sometimes it goes bam, it goes a huge boost, and that extinguishes that premixed flame. Okay, and then it does this, and then maybe the flame wants to start burning again, and then every few seconds or milliseconds, you get another burst in the dissipation rate, and it extinguishes. Okay, so that's again is one of these examples where you see that these very rare events can have a huge impact dynamically, and LES sometimes is able to capture that and run. Another example here is this, and unfortunately I was too lazy to put in the movie. In the break I'll put in the movie, I'll show you the movie afterwards. But this is a simulation, that's interesting. So this is a simulation of this was another one of these flames that were considered in this TNF workshop. So many people in the world did simulations for this. The configuration is shown here. This is a bluff body stabilized flame. This here is the flame holder. You have an airflow around this, and then you have a fuel flow through this very, very tiny nozzle here in the center of this white surface. You can see this. There's a black spot there. That's the fuel nozzle. And the white surface, that's actually just a solid body. So what you get then is, so this is a jet, a fuel jet, and then you have the air coming around, and it forms recirculation zone here, and it forms another recirculation zone here. So it's quite a complicated arrangement here, and so on. So what I'm showing, so we use a simple combustion model here, flamelet model, and you see here the temperature and the CO mass fraction. This here is very close to the nozzle, and this here is again temperature and CO mass fraction, and it's very far downstream. Okay, so one is here and one is here, and you see the agreement with the experiment. Simple model. Turns out nobody else was able to get these agreements. Okay? Most people had either good agreement very close to the nozzle or downstream, depending on how they tune these coefficients in the K-epsilon model or in their combustion model. And not in the combustion model, so in the turbulence model. Okay? And so the point was, most people, or everyone else, was using RANS. Okay? And it turns out, if you use a very simple combustion model, but you do LES, you get the right result. And you had to be a little careful. We had to develop a new technique here for how to build the mesh and how to design the filter, the LES filter, which was the clue here in this paper. But the point is, so the question is, why do we get the right result if you don't get it right? And what you see, when I show you the movie later on, is that you see here, there's a shear layer, very strong shear layer, because you have a recirculation in here, and then you have a very high-speed flow outside. So you get this shear layer, and this shear layer, you see, is pretty stable. Actually, it breaks down only about here. This is where you get where the flow starts to go back. And it does that for a long time. It just stays the way it is. And then once in a while, not very often, just once in a while, the whole thing breaks down already very close to the nozzle. So by doing that, you bring in a lot of air. The residence time in here is very high, so that air that stays around for a long time, and that makes a difference. And so, again, there's a case where something happens only once in a while, very, very infrequently, but it has a leading order effect on the results. Okay? So it's not the combustion model that's so great. It's just the simulation picks up these random events which you can do in LES, you can't do in RANS. Okay, so we talked earlier about PDFs and a transported PDF model. In LES, there's something similar. It's called the FDF model, filtered density function model. There's a difference between this filtered density function and the PDF, and that difference is, I think, is important to realize, and that is described here. I don't want to go in these details, but if you have an interest in these subtleties of these models, then you should look at this. So I'll skip this. This is another thing I want to skip. I mentioned that very often the models that we use in RANS and LES, they're very similar. And then sometimes they're different. And so one example is that we said earlier the dissipation rate and the scalar variance, they're very important. And in RANS, we saw yesterday that for the scalar variance, typically you solve the transport equation. And then there was this timescale model, which we have here again, this timescale model that we use to model the dissipation rate. In LES, turns out, usually we do the opposite. We use the timescale model for the variance. And then the scalar variance transport equation, we use that to actually determine the dissipation rate. That's shown here. This shows these different models. But this was just meant to be an example. I mean, these are important quantities, but it was just meant to be an example for how things sometimes are different in LES and RANS. And the main reason why they're different is that in LES, again, you have different opportunities. You have different information that you can use to your advantage. Okay, so I showed you some simulations of these flames just to show you maybe one example. I mean, several groups here have developed codes that you can use for real combustion devices. And one thing that's really, really important is that you cannot take a RANS code and just make it LES. The reason is this. In RANS, you typically get very smooth solutions, as I showed you earlier. And because of that, you can have really bad meshes, and you can have you can add numerical diffusion to codes and so on. It doesn't really change change the solutions all that much. However, in LES, that's not the case. In LES, you want to resolve these very tiny, smallest fluctuations, and any amount of numerical dissipation, might destroy that, might destroy these fluctuations. Now, LES is very expensive. Why is it very expensive? There are two reasons. First of all, and I haven't said this yet, RANS simulations for a jet flame, you would just do a two-dimensional simulation because the equations, they are axisymmetric. I mean, the solution is axisymmetric. So you can make use of that and just do a 2D simulation for a 3D field. Okay? In LES, that's never possible. Why is that? Because turbulence is always three-dimensional. I talked yesterday, I talked a lot about this energy cascade, how large scales transform into smaller scales, transform into smaller scales, and so on. That mechanism is based, it depends on the nonlinear term, the nonlinear processes, and it's there's a mechanism of going from large scale to small scale. It's called the vortex stretching mechanism. And it turns out, can easily show this, that the vortex stretching mechanism, it lives only in 3D. In 2 dimensions, there's no vortex stretching mechanism. You can think of it like this, here vortex, then there's vortex, it goes like this. So this is a motion in 2 dimensions. If I want to stretch this vortex, I have to stretch it in the 3rd direction. Okay, so a very simple picture. It shows why turbulence only lives in 3 dimensions. So if you want to resolve the turbulent motions and you want to resolve these dynamics of the vortex stretching, your simulations always have to be in 3 dimensions. There's no LES in 2D. Okay, that's number 1. Number 2 is now we could say, well, sometimes if I have complex geometry, I always need to do 3-dimensional simulations anyways. Okay, so is LES then more expensive? And yes, it is, because these small eddies that you resolve, they have small timescales also, and you need to resolve these timescales. So very often in LES, you have to have very, very small time steps, and especially if you think about simulations of a piston engine. Okay, that piston, it moves relatively slowly compared with the motion of the small-scale turbulence. So you have to not do, have step sizes that are of the order of 1 crank angle. You have to have step sizes which are on the order of, your smallest turbulent timescale, which might be much, much smaller. Okay. So these simulations are always very expensive. And if you do a very expensive simulation and you have to add a lot of numerical dissipation, then your solution will be as bad as Rand's solution, but you pay for an LES solution, so that's not very good. Okay? So it's very important. Numerical methods are very, very important in LES. And one problem now is, okay, you have lots of little fluctuations, and you don't want to over-resolve these. You have only a few cells to resolve these smallest fluctuations. If you have no dissipation, then this might, if you have central schemes, this might lead to dispersive errors, if you get overshoots and undershoots and all of that. So one has to be very careful with numerics. And a few people have these codes here. The French here, Surfax has a code, Stanford has a code, and there's probably many other, or several other codes. This is a simulation, just a picture of a simulation we have done for an aircraft engine a while back. You see here the liquid spray, and you see here combustion, and this is just supposed to look nice. And but more recently here, we have done simulations, for example, of soot formation in this thing. And in these simulations, again, what we found was that soot is very intermittent. What's interesting in soot is most of the time you don't see soot at all. And then all of a sudden you see a big cloud of soot. Okay? And again, with the Rand model, you can predict this, which is why the aircraft engine manufacturers, they're very eager to get good soot models. And you see here, we did simulations compared to the experiment. It doesn't look all that bad. Okay? Not perfect, but it doesn't look all that bad, especially if you get the trends right. So I could, show you more details of this, but I guess in the interest of time, we'll skip this and move on then, again, to more fundamental questions. Yes?
So you're talking about 3D motion. So who gives you quick to run a 2D LES versus science? So what would be your...
I think it's wrong. That's what I think. I mean, it's just like we do a lot of 2D VNS, okay, with full chemistry. Why do we do this? Because it's just awfully hard to do 3D. And you have to understand that in a 2D DNS, your small scales, they're bad because the energy cascade in 2D, it actually goes the other way. Okay? Again, it's the wrong side here. So we don't call this turbulence, we call it, interaction with some vorticity with a reactive flow. That's all that you should call it, and that's what you should call this. I wouldn't call it real physics. Yeah. Okay? Are there other questions? So what's the time situation? Okay, so we have a few more minutes. Now, there's the lunch situation again. Lunch situation today is this. you guys have, let's say, lunch at 12:15, but then there is this panel again at 1:15, and that with all the lines, and so that doesn't make leave enough time really. And so we were asked to cut the break this morning a little bit, and then let you go earlier. Okay, so you don't lose anything. You don't have to work more. We just shift your free time from now to later. Okay. And I said to Professor Long, I said, whatever the boss tells me, that's what I'm going to do. And so that's what we're going to do. So we make the break a little shorter, and then we let you go a little early for lunch. Okay, so we want to go back to talk a little more about now the details of premixed combustion and non-premixed combustion. I said earlier, we'll talk about non-premixed combustion only briefly because it's not all that complicated, or not as complicated compared to premixed combustion. Premixed combustion is a lot more complicated. And so, so we want to talk about now here, lecture 11. We want to talk about some of the relevant physics of premixed combustion. Lecture 12 then, we'll talk a little more about the G equation model, and we'll cut this a little short because I think it's much more important to understand really the physics, the turbulence chemistry interaction physics, than to look at these models in all the little details. And then 13 again will be on models for the laminar burning velocity, and they are also this has two parts. One is a very fundamental, I think very elegant, interesting part, and then the other one, is a specific model, and we'll cut that short. Okay, so we want to talk about these regime diagrams for premixed combustion, and you might have seen these, and it's very important to understand these. It's important to understand the physics of these in the different combustion regimes. And so what these regime diagrams, what they do, essentially, they tell you something about the interaction of turbulence and the flame. And what we said earlier is you could have a regime where the flame is infinitely thin compared to the scales of the turbulence, but you could also have a regime where the turbulence scales are very, very small compared to the flame scales. And in both of these regimes, of course, the interaction is very, very different. The physics are very, very different. Okay, so that's expressed in these regime diagrams, and in order to look at these regime diagrams, it's good to just assume unity Schmidt number, which means we can always replace kinematic viscosity with diffusivity or vice versa. And then we define the flame thickness here like this. LF is D divided by SL, and flame time here is D by SL squared, which reminds me, I still owe you I owe one of you a cigarette lighter. Who gave me the cigarette lighter? I bought one here. Oh no, this is your empty one. Yeah, I bought one yesterday. Okay, and then I owe you also there was this question about the flame thickness of hydrogen. Somebody said, is a hydrogen flame thicker than methane or vice versa? And I wrote something like this down, but I wrote the wrong quantities down, and yesterday it occurred to me that I used the wrong quantities to make the argument. Actually, I said I'm going to compute it real quick, but I didn't have the right stuff on my laptop, and I couldn't. And I asked one of my students this morning to send us a plot, and we'll see. But really, I think I used the wrong quantities to scale, because the quantities I used the time scale, but we don't know the time scale really. But what we do know is the diffusivity, and we know the flame speed, okay? So if we scale it like this is why I just remember this. If we scale it like this, then we know the diffusivity of a hydrogen flame, or of hydrogen, compared to methane, is about 3 times larger. Okay? Lewis number of methane is about 1. Lewis number of hydrogen is about 0.3. So this would be about 3 times larger for hydrogen flame, And the flame speed, also we know, I don't know exactly what hydrogen was, but it's 150 or whatever. And methane is 40. So this is, let's say, I don't know exactly, but it's more like a factor of 5. Okay? So you see that although the diffusivity is larger, because the flame speed is even larger, it means that the hydrogen flame is thinner, which is what I said last time. We just didn't have a good argument. And we'll see. So this now just comes from scaling. And once we get the plots, maybe I'll check in the break. What are we? No, we're six. Yeah. So they are 6 hours ahead of us in Germany. So he should have had enough time to make this plot. So maybe we get it in the break. Anyways, good. Let's get back to this. So we have these scaling relations here. And what's interesting now is we can say, so look at this. This basically says the diffusivity, or nu, is equal to d. Okay? But d is equal to LF times SL. Okay? So if I want to write the Reynolds number, which is u prime times L over nu, I can write it like this. U prime, or v prime, times L over nu is equal to d, and d is equal to SLLF. Okay? So that's the Reynolds number using the scaling argument. What's nice about this is that you see now we express the Reynolds number as a velocity ratio, v prime over SL, and the length scale ratio, L over LF. Okay? So that's good. Then we have the Dampköhler number. And the Dampköhler number is the ratio of the timescales. The Dampköhler number is the flow timescale over the chemical timescale, or flame timescale. Okay, so F means, I don't know, this does not mean flame. Oh, I should write it like this then. Okay. Flow timescale over flame time. Okay, so you should know this. You should not be confused. Okay, so time scale then, look at this. The flow time, no, this is a flame time scale. Flame time scale now. Here can be written flame time scale. So we want to write this in terms of LF and SL. And then time scale would be equal to LF divided by SL. Okay? So LF divided by SL, you see that's in the denominator. And then a flow time scale of the turbulence here, that can be written as L divided by V prime. Okay? So you see it's the same quantities as what's up here, or the same ratios, V prime over SL and L over LF, but a little different. Okay, so it's the Reynolds number, Dampköhler number, and then there's another one here, which is the Karlovitz number, and that's a very important quantity, as you would see. The Karlovitz number is the ratio of the flame thickness, is the ratio of the flame time and the Kolmogorov time scale. Okay? Why do we look at this ratio? I'll show you in a minute. Because we said earlier, let's say the chemistry is fast, okay, or it's not fast, whatever, but it has a certain time scale. And now we have the turbulence, and that turbulence that tries to destroy the time scale, the flame. Okay. However, if the time scale of the turbulence is much longer than that of the flame, it cannot do anything to that flame. Okay. So we want to look at what is the shortest time scale of the turbulence, and we want to see is that short enough to do something to the flame. Okay. The smallest time scale in turbulence is the Kolmogorov time scale. And so this means if this Karlovitz number here is very small, which would mean this is very large, then the turbulence cannot do anything to the flame. And if this is very small compared to this, then the Karlovitz number will be very large, which means the turbulence can destroy the flame. Okay? So TF over T eta, we can write this again in terms of length scales or velocity scales by assuming by using relations here like this, because the D appears in both of these and drops out. What's interesting then, the timescale argument, I think, is usually when we, in physics, we always compare timescales. Sometimes it's more intuitive to compare length scales. And so when we think of the you see the Karlovitz number is actually, it's defined with the timescales. However, it can be expressed here as the length scale squared. Okay? So Karlovitz number, so a Karlovitz number larger than 1 means that the Kolmogorov scale is smaller than the flame. Okay? Karlovitz number smaller than 1 means even the smallest eddy of the turbulence is larger than the flame, and so it cannot penetrate the flame. Okay, so Karlovitz number, that's the most important one actually that we have to talk about.
Is there a reason why you can square as
Yes, you can just replace. Maybe it's even shown here. No, but you would have to replace. You can express this in terms of the other quantities, and then what you will see is just like this. And then what you will see is that you in both the numerator and denominator you get this d, and that drops out, and you know what's left is then as a squared here somehow. Right? If you you could probably start here from this and put in the SL here, and then you get an LF squared. Right? Okay, so so these are these quantities. You can skip this here actually, but what's important is you have the Reynolds number here in terms of this. You have the Dunkel number now in terms of these velocity and length scale ratios. If the Karlovitz number also, you know, appears as a ratio like this, and then the Karlovitz number here can be expressed as function of Reynolds and Dunkel. There's one more we want to introduce. Let's see where we are with time. Let's just yeah, do a few more minutes, and then. So what did he say again? We should cut this now by 15 minutes, and then let you go 15 minutes early. So we'll stop at 10:30. Can we do that? 10:30, and then continue at 10:45. Yes.
I have a question regarding the Dunkel number. Like in an non-perfect sense, I kind of understand that it's like a fixed time over the chemical time, which would be very important when making a stable something. This definition that you gave is like different. And in the mixing time, in the premixed sense, I don't really understand it.
No, you might think of the mixing time. Don't look at the combustion process. The mixing time is just the time scale of the turbulence. Okay? Okay, so I did confuse you here with my.
The flow scale, not the mixing scale.
The flow scale, right? Or
Is that only premixed sense? Because a non-premixed is the mixed one.
was that?
In non-premixed sense, it's the mixed one, the mixed time scale. It's not the flow scale.
Well, you should always look at the. You're making a good point. I mean, it turns out, and I think you know you feel this deep in yourself. You feel this. It turns out the Dunkel number does not have much of a significance in premixed combustion. You know, still, when you look at these early regime diagrams, they always show the Dunkel number. In LES, then again, the Dunkel number has some meaning, but the Dunkel number has not. See, the Dunkel number looks at the. Okay, so let's do this differently here. So this here would be flow, and this here would be flame. See, even FL wouldn't cut it. So the flow timescale here, that is the timescale of the large-scale motions. Okay? And the large-scale motions, how these interact with a small flame, that doesn't matter actually too much. What's much more important is how do the small scales interact with the flame. That's the Karlovitz number. So the Karlovitz number is like the Dunkel number, but defined at the appropriate scales.
Okay. And the second question is, what the scaling relationship results from the flame thickness comes from laminar theories, if I'm not wrong. Does it hold like the same kind of analogy for turbulence? Like it's
You should look at this. You should look at this really as what you get from a laminar flame. I mean, see, you have a laminar flame, and that has this relation between SL and the and LF and diffusivity and all of that. And then on the other side you have the turbulence. Okay, and now we just want to compare how these interact with each other. That does not mean that if they have a very strong interaction and the turbulence actually destroys all the flame, that does not mean LF still holds in that regime. It just tells us if this was the laminar flame, this is the turbulence, I compare the two to each other, and if I see from this that the turbulent timescale is much smaller than the flame timescale, then the laminar flame will not be a laminar flame. Okay. So sometimes we use these LF and so on. We use these just to define, for example, a chemical timescale. Okay. So there's another Karlovitz number here that is used, and that comes because of the following reasons. Or maybe I just move this up. That comes because of the following reasons. If you remember what we did earlier, we talked about premixed combustion. This is the temperature as function of x. There's a premixed flame. Then we said there's a very thick preheat zone. And in that preheat zone, you have no chemistry going on. Okay? And then we have a thin reaction zone. And all the chemistry happens in this thin reaction zone. Okay? We say the length scale of this is delta. And the length scale of the whole thing, that's NF. Okay? Now, one argument you could have is, hey, if all the chemistry happens just in delta, and the preheat zone, there's no chemistry, why do I care if the chemistry, if the turbulence interacts with the preheat zone? Okay? The real question is, so Karlovitz number smaller than 1 would mean now the turbulence scales are smaller than the preheat zone thickness, and they can mix in the preheat zone thickness. But they might still be a lot larger than the reaction zone, and maybe they don't do anything to the reaction zone. Okay? And what happens in the reaction zone, that's really important. Okay? So there's a second Karlovitz number. The Karlovitz number looks at how does the Kolmogorov scale compare with the flame thickness. And there's this Karlovitz delta that looks at how does the Kolmogorov scale compare with the inner layer thickness or the reaction zone thickness. Okay? And we'll see later on that this is important. So Karlovitz delta is delta squared over eta squared. And so that is a delta squared times the Karlovitz number. It turns out that this delta, the reaction zone thickness, is roughly 1/10 of the preheat zone thickness. And so we typically say Karlovitz delta, that's about 100 times larger than the Karlovitz. Okay. That's about 100 times, right? Right. So that's about 100 times, so 0.01 times the. That's about 0.01 times the Karlovitz, right? Okay. Factor 100 between the two. Okay. So this means now, from this I can plot my regime diagram, because now you see I have expressed all of these different quantities. I've expressed these in terms of. Well, I haven't done this for the Karlovitz number yet, but that's shown here. But I can express all these quantities as function here of V prime over SL and L over LF. So for example here, Reynolds number is V prime over SL times L over LF. And now if I plot a diagram, if I want to plot a diagram that has V prime over SL on one axis and L over LF on the other axis, then I have an expression here that gives me the functional dependence that says V prime over SL is equal to, so V prime over SL, that's equal to LF over L, or L over LF to the minus 1, is Reynolds number times L over LF to the minus 1. Okay? So in a log-log plot, that would be just a line. So I set Reynolds number equal to 1. Then this would be the Reynolds number equal to 1. That would be just a line with a slope minus 1 in this log-log plot. Okay? Now it kind of looks like this. So I can, I can plot the, so now in this regime here, the Reynolds number is smaller than 1, which means it's laminar. In this regime here, it's larger than 1, which means it's turbulent, and so on. So and I can do the same thing with all the other quantities. I can do the same thing with the Dunkeler number. You see that will have a slope of +1. So it, kind of comes out like a +1 slope. You can do this here with the Karlovitz number. I set the Karlovitz number equal to 1, and I see V prime over SL. Or let me show you the Dunkeler number here looks like this then. And then you have the Karlovitz number here. You see V prime over SL is equal to this. Set this to 1 now. L over LF to the 1/3. So that's a line with slope of 1/3. Kind of like this. So this here is Dunkeler 1. This here is Karlovitz 1. And this here is Reynolds 1. Okay? So then what you see in this regime diagram is Karlovitz 1, Karlovitz larger 1. This means in this regime, actually the turbulent, the Kolmogorov scale is smaller than the flame thickness. In this regime, it's larger than the flame thickness. And this is Karlovitz delta equal 1 is about here or so. So this is Karlovitz delta equal 1, and so on. So this is how we plot these regime diagrams. And then the different regions in this diagram, they correspond to the different regimes. And then the physics are different in different regimes. And then after the break, I guess, we'll talk about what the different physics in the different regime is. Okay, so I'll let you go. I'll be here in case you want to ask questions.